Okay, we are now going to talk about chiral molecules, which is somewhat complicated. So you need to be completely focused when you're listening to this. In the past, we've talked about isomers, and we learned that isomers are something with the same chemical formula, but they arrange differently. For instance, with ethanol, there's 2 carbons. With dimethyl ether, there's 2 carbons. There's 3, 4, 5, 6 hydrogens. 3, 6 hydrogens, and 1 oxygen. They have the exact same chemical formula, but they're arranged differently. Now we're going to do something a little bit more specific. And we're going to look at the individual carbons. And these are called stereoisomers. They have identical molecular formulas, but they are not structural isomers. They have the same atoms bonded to the same carbon, but they're arranged differently. In order to have this happen, and this is really important, 4 different things on 1 carbon. You have to have this happen in order for it to work. For instance, if you have carbon, hydrogen, bromine, chlorine, that does not work. It would have to be carbon, hydrogen, iodine, bromine, chlorine. You have 4 different things on that carbon. Another example would be carbon to a methyl group, to an ethyl group, CH2, to a hydrogen, to maybe propyl. Even though they're all 3 carbons, this is a propyl, that's a methyl, that's an ethyl. They're 3 different arrangements. So there's 4 different things here total. We are going to attempt to watch a video to describe this a little bit more in detail. So when we're looking at this, here's your left hand in space. If we put it in a mirror, here's our right hand. However, if we try to overlap our left and right hand, it wouldn't work. When they talk about being superimposed, what they're talking about is whether or not they can overlap.
Many molecules, including important drugs and natural products, are chiral. This is a ball and stick model of a carbon molecule with 4 different groups attached to the central carbon. For example, the 4 groups could be hydrogen, chlorine, methyl, and carboxylic acid.
Notice once again, they are 4 totally different things here. If 2 of them are the same, it won't work.
Molecule is chiral. That is, it is not superimposable on its mirror image.
They are dropping down a mirror in this process, so that way you can see the mirror image. Notice that the purple one is closest to the purple one in the mirror, just as if it was in a mirror. If you were looking in a mirror, things that are closest to the mirror, you will see more prevalent. And here's the green one, and it's further back, just like if it were in a mirror.
The 2 forms of a chiral molecule are called enantiomers. Using special rules, one form is labeled R, the other S. Enantiomers have mostly the same physical properties, but they behave differently in chiral environments.
Notice when they overlap, the green and the purple are coming together, rather than the purple and purple. Up here, the whites are overlapping. Back here, the yellows are overlapping. But in the front, the green and purple. Because of that, that means it's not being superimposed perfectly. It's not overlapping perfectly.
Molecules may contain more than 1 chiral center. For example, tartaric acid, which is found in many fruits.
Notice with this example, we have carboxylic acid here, a hydrogen on the right, and OH on the left, and then we have this down here. 4 different things on the same carbon. If we look at the next one, this carbon here. So when we're talking about chirality, we're looking at one carbon at a time. That's actually really important. Some people don't realize this. We're not talking about the whole molecule. Looking at one carbon at a time. Hydrogen OH here, this whole thing up here, and COOH down there. Okay, so let's go back to our PowerPoint. Hopefully that was able to clear some stuff up. So when we're looking at this, we have a left hand and a right hand. If we try to overlap our hands, we'd have a thumb here and a thumb here. You cannot overlap them perfectly. And that means that our hands are chiral because they don't overlap perfectly. So if we're looking at some other common examples, we can't overlap gloves. You'll notice when your right glove is on your left hand, that won't work. That's chiral. A golf club. There's a reason why we have left-handed golf clubs and right-handed golf clubs because they're not the same. You can't just flip it around. However, with the ball, notice that one side is the same as the other. You can actually superimpose those two. Same with the glass. That's why these are achiral. Once again, you can't put your left shoe on your right foot. And we also have left-handed and right-handed scissors because you can't reverse them. So when we're talking about the mirror image, this goes back to that video we just watched. Notice 4 different things. That's what you want to look for. So that means when you superimpose it, notice here's the mirror image, so the chlorines closest, bromines are furthest away. We overlap them. The hydrogens and the iodines are okay, but when we overlap them, the green goes over to the brown. Those don't overlap. That's why it's chiral. If we have 2 of the same things on it, okay, here it is, and we might be able to say, okay, the H's match up and the bromines match up. But if we flip this around, it's gonna be able to be the exact same molecule. You'll be able to overlap them. You might argue that if you flip that one around, you might be able to, but you can either play with molecules or you can just take my word for it. It's up to you. But the angles are not going to be the same. They're not going to be able to be overlapped. So when we're looking at chiral or achiral, what you're looking at is whether or not you have 4 things that are the same. 1, 2, 3, 4. These are 4 different things. Even though these are both carbons, this is ethyl, this is methyl. This is chiral because they're all 4 different. B, we have hydrogen and hydrogen are the same. So that's achiral. And C, we have 4 different things, meaning it's chiral. Now we're going to talk a little bit about Fischer projection because we're going to talk a lot about it in the next chapter, so we want to have a little bit of an introduction to it. It's basically a 2-dimensional way, a drawing of a molecule. The most oxidized group is on top, which usually means a carbon-oxygen double bond is going to be on top. Vertical lines are representative bonds where they cross. That's the carbon. And I'll show you a picture of these in a second. Horizontal lines means that they're coming forward. So here we go. These are the Fischer projections here. Notice that the double bond is on top. That's what they mean by the most oxidized. Here's the bonds. Where they intersect is a carbon. These are coming out towards you, where these are kind of going out behind you. Typically, that's going to be a chiral carbon where they cross. meaning that they have 4 different things on the same carbon. Notice this L and D. They're looking at the very last line. So here's the most oxidized. The last cross of the oxidized, if the OH is on the left, it's an L. If the OH is on the right, it's a D. And that's just another way of explaining what kind of compound it is. So once again, here's the Fischer projection. There's the most oxidized. You go down the list. A lot of times, they'll have several of them. You want to look at the very bottom one. OH is on the left, so it's an L. The OH, the last one, is on the right, so therefore it's D. That's all you have to look at is the bottom line. So, indicate which pair is a mirror image. You're looking for 4 different things on the same carbon. Those are what's considered enantiomers. So 1, 2, 3, 4. There's 4 different things here, so these are the mirror image, which are also called enantiomers. This has hydrogen as the same, so these are not mirror images. Alright, and we are going to talk more about the D and L in the next chapter.